In this video, we shall make progress to learning how to find exact values of areas on the normal probability curve. And I'm going to be deploying the strength of technology, namely StatCrunch, in order to compute exact probabilities or areas under the normal probability curve. So using technology, I like to calculate not approximations anymore, but exact probabilities for normal distributions with the following parameters. So if it's a normal distribution, based on what we have done so far, I can sketch a normal distribution in this way. And the mean is always what? The average value, which is usually in the middle. So I'm going to put 5 here. The standard deviation, the measure of average spread, is your equal to 1, and I'm required to find the area bounded by 0 and the upper end by what? 6. Okay, so based on this is not drawn to scale, as a quick disclaimer, and in this case I am interested in the area bounded between these two values. To find the exact probabilities, I'll go over to StatCrunch. Since I want values between two values 0 and 6, I'm going to toggle this over to between. Again, just a quick reminder how to get to this point. Let me close out of this. You go to Stats, you go to Calculators, and then you go to Normal Distribution Calculator. I want to capture the size of the area between two values. I'll click on Between. And the first parameter here is the mean, which is the center value, 5, and the standard deviation is 1. So I'm going to do 5 and 1. And I'm interested in particular in the area between two values. So this seems to be given. Okay, there we go. And I'm interested in the area between 0 and 6. And I can compute that area. So between 0 and 6, it is 0.8413. So probability that x lies between 0 and 6 is 0.8413. For the next question, you might notice that the only thing that has changed is the standard deviation. I want to illustrate here that it is important to be careful to plug in the right values, because just a singular value change could mean a heavy change in values, as we shall soon see. So in this case, the mean is still 5, but the standard deviation is no longer 1, it is now 3 in this question. And we're interested again in the probability between 0 and 6. So again, I am going to do this. That is off. So I'm interested in the area between those two values. And what would that be? I'll only need to change the value of 1 to 3 and compute. And you'll notice that I have a totally different value from what I got earlier. So it is important to be careful when we plug in the values for the parameters. So you have 0.5828. Then next, I have another normal distribution where the mean is 1 and the standard deviation is 3. I'm interested in computing the area where values of x are greater than 4. So 4 is a threshold. I'm going to locate 4, and I'm interested in the area above 4. So that'll be the area to the right of 4. And let us compute that probability or proportion of values of x above what? 4 in this case. That will be equal to, let us go to our exact calculator. I no longer need between because I don't have two endpoints. This time I only have one endpoint, I only need the standard case. So what is the mean in this case? That will be equal to 1, and the standard deviation is 3. That's already here. So, but I want the area above in this direction. So I'm going to change this to greater than or equal to. Greater than or equal to 4. And that is 0.1587 to 4 decimal places if I want. And take note that this is greater than and this is greater than or equal to. For measured quantities, equal to 4 and greater than is approximately the same as greater than 4. Then for the final one here, we have a normal distribution where the mean is 6, the standard deviation is 2, and I have my random variable x. I'll locate my threshold, which is what, 3, and we want less than 3, so this time I want the area to the left of 3. So I can find that area in exact terms by heading over to StatCrunch or keying the parameters for the normal distribution, which is 6, and the standard deviation is 2, and I'm interested in the area to the left of what? Less than 3, and compute. So this will be 0.0668. Let's see more. Let's see if we have more questions. Here we're looking at inverse normal probabilities. I want to introduce a case where rather than supplying these three values, the mean, the standard deviation, and the value here, so that StatCrunch helps us to compute the probability, could we provide StatCrunch with the probability so that it provides what? The threshold values for us. That is the idea of finding inverse normal probabilities. And this example will illustrate that. You see, in this example, we are told that the distribution of passenger vehicle speeds traveling on Interstate 5, I-5 in California is nearly normal with a mean of 72.6 miles per hour and a standard deviation of 4.78 miles per hour. So if I were to sketch that, I'll have a normal distribution, a sketch, not drawn to scale, and the mean is 72.6 and the standard deviation is 4.78. Question A. What percentage of passenger vehicles travel slower than 80 miles per hour? So our X here represents what? Speed in what? Miles per hour for different vehicles speeding on I-5. So in this case, I am looking at the same distribution with a mean 72.6. In fact, I might not need to do this. Let me just use um, my calculator to work on this. So I'm interested in the probability that x, the speed, is slower or lesser than 80 miles per hour. So what would I do? My mean is 72.6 and my standard deviation is 4.78, and I'm interested in less than 80, so less than 80 and compute. So I have 0.9392. So this is equal to 0.9392. The next one says what percent of passenger vehicles travel between 60 and 80 miles per hour? That will be the probability that the speed x is between 60 on the lower end and 80 on the upper end. For between, I definitely need to switch to between. And I still have my parameters here retained by StatCrunch. And I only need to indicate the lower end, which is 60, and the upper end, which is 80. And I have 0.9350. Okay. And the next question says, how fast do the fastest 5% of vehicles of do the fastest 5% of passenger vehicles travel? This is where the idea of inverse probabilities come in. So I'm going to go ahead and sketch the normal distribution from what we had earlier. And what do I want? I want the mean, which is 72.6, then the standard deviation, which is 4.78, and we want how fast are the fastest 5%. The fastest 5%, should they be on the lower end of the speed or on the upper end? What do you think? I would say that they should be on the upper end since they're the fastest, and X here, the speeds, should be talking about the larger speeds. So if I were to shade this part, so I want the fastest 5% up here, which means I'm already given the area. What I'm finding is the threshold or the cutoff for the upper 5% of speeds away from the lowermost 95%. So to do that, I can use StatCrunch. Since I'm not looking at areas between, I'm going to switch back to standard, and then my parameters remain 72.6 and 4.78 for the mean and standard deviation respectively. And I want the area above an unknown value. Since it's above to the right, I'm going to switch this to above an unknown value. So I'm going to erase that. And what percentage? I want it to be 0.05, which is 5%, and compute. So this is telling me that 80.46 is the number here that separates the upper 5% of all passenger speeds from the lower 95% of all passenger speeds. So this is 80.46 miles per hour. Then question D. The speed limit on this stretch of I-5 is 70 miles per hour. Approximate what percentage of passenger vehicles travel above the speed limit. Well, above the speed limit, that's above 70. So the percentage or the probability of X speed above 70. In this case, I will need to make sure I'm in standard mode since I have only one value. And this time I am supplying the value above 70. What probability are we dealing with here? We have 0.7068. So this is 0.7068. So about 70.68% of all vehicles travel above the speed limit of 70 miles on I-5. All right, here is an application problem. In this problem, we're told that Wendy's drive-through fast food restaurants spend quite a bit of time studying the amount of time cars spend in their drive-throughs. Certainly, the faster the cars get through the drive-through, the more the opportunity for making money. QSR magazine studied drive-through times for fast food restaurants and found Wendy's had the best time, with a mean time spent in the drive-through of 138.5 seconds. Assuming drive-through times are normally distributed with a standard deviation of 29 seconds, so that means that the variable of interest here that we're observing for the different cars are the drive-through times. And we have to assume that it is normally distributed. So if I were to draw that, I'll sketch a normal probability curve. My x variable here represents the drive-through times. And since they are normally distributed, I'm interested in the parameters. The mean time is 138.5 seconds. And then the standard deviation is 29 seconds. And our interest is what is the probability that a randomly selected car will get through Wendy's drive-through time in less than 100 seconds. So we want probability that X the drive-through time is less than 100 seconds. So I'll locate 100 on the horizontal axis, and I'm interested in the area below 100. So that'll be to the left of 100. So going to my calculator, I'll key in the parameters of this distribution, the mean being 138.5 and the standard deviation being 29 seconds. And we want less than in particular, and we want less than 100. That gives me 0.0922. That is the size of that area. Let me erase this. And so we have the size of that area is 0.0922. The next part of the question says, what is the probability that a randomly selected car will spend more than 160 seconds in Wendy's drive-thru? Which means for the same distribution with a mean of 138.5 and a standard deviation of 29, this time we're interested in probability that X, the time spent in the drive-thru, will be more than 160. I will locate 160, which should be to the right of the mean, and I'm interested in the area above 160, which means the right of it. And I'm interested in the size of that area, the proportion of drive-through times that meets that criteria. So I will change this to greater than or equal to 160 and compute. And I have 0.2292. The next part of the question says, what proportion of cars spend between 2 and 3 minutes in Wendy's drive-thru? What is particular about this question is that the unit of measurement of time has slightly changed to minutes. Well, so far we've been measuring, the parameters were measured in seconds, and so you have 138.5 seconds and 29 seconds. So converting 2 minutes to seconds, you have 120 what? Seconds. And 3 minutes to seconds, that 180 seconds. So proportion, the drive-through time is between 120 and what? 180 seconds. What would that be? So this time we go back to activate the between 120 and 180 and compute. And in this case, you have 0.6620. And the last question here says that suppose Wendy's wants to institute a policy at its restaurants that it will not charge any patron that must wait more than a certain amount of time, which we do not know, for an order. Management does not want to give away free meals to more than 1% of what? The patrons. What time would you use data to prove, to advertise as the maximum wait time before a free meal is awarded? It's a great question. So let's visualize the distribution. The mean wait time is 138.5. The standard deviation is 29. Now there are different values of X, the wait time, or the waiting time before a free meal is awarded. And our interest here is there is a particular time where if a patron has to wait more than that time, they get a free meal. Well, who are those waiting the most? Are those on the lower end or on the upper end? What do you think? Lower end, that's small wait time. That's good. But higher end would be much waiting time. That's not very good. So we want these people to come back. those who have to wait longer. So we're going to placate them, and we only want to capture the top what? The top 1%, because that's what management says they can afford. So we want this to be 1%. So what is that threshold? What method would we use this time? Are you thinking along the lines of inverse normal distribution? I would say yes. We already have the parameters of the normal distribution here. I'm only finding a single value, so I don't need between. So I'm going to switch to standard. And I'm interested in the area above that is greater than. So I'm going to keep greater than, but I don't know greater than what value. Greater than what value. So I'm going to keep this blank. But I know that the proportion I want to capture is 1%, which is same as 0.01. So compute. This is saying that that value I am searching for that separates the upper 1% is 205 point what? 96 seconds. So back to the question. The time I would recommend Wendy's advertise as the maximum wait time before a free meal is awarded, and I'll still meet I'll still align myself with what management wants, is 205.96 seconds.